Okay, so now I think we're good to go for real stuff. After all these technicalities, we can do our first algorithm, which is called time evolving block decimation. And it's an algorithm that was put forward by Guiffre Vidal, sometimes called TBD. By Vidal in 2003, so it's in a way a much more recent algorithm than the MRG. But it's a do-it-all algorithm in a way. It's not the best at anything it's doing, but it does many things and very simply. It's an algorithm to essentially you can use it to apply quantum gates to an MPS. I think that's the simplest way to see it. Apply quantum gates to an MPS. So you can imagine a quantum circuit, but via trotterization. This gives you access to all real-time evolution you would potentially like to do. Because if you can apply gates, then you know that by trotterization, any local Hamiltonian, you can write the infinitesimal unitary associated to it as a brick wall circuit of gates. Or another way to see this statement is that every real-time evolution of a quantum system can be simulated on a quantum computer with discrete gates. Well, take these discrete gates and apply TBD to them, and that will do a real-time evolution. Of course, here, these gates are special in the sense that if you do trotterization, they are going to be very close to the identity. So they are usually nice gates, okay? They are very close to the identity. Okay, what is the starting point of the algorithm? It's a very easy algorithm. It's fully local in a way. The starting point is an MPS in canonical form. So you start from a certain MPS in canonical form. You don't integrate back the singular values to any spot. So, and what we do is now so this is our initial state, and now we apply a first gate. Either a gate because we want to run a quantum circuit on it, or gates from trotterization of a real-time evolution we care about. So the gate is something that generically, I will assume it's just 2 qubit gates here, okay, that I have 2 local gates. And now what I'm going to consider is I'm going to work on the tensor here. Okay, I'm going to take like this tensor. This tensor is the one I will work with. And my objective is to put back this state in canonical form. Now that I applied this gate, it's no longer even clear it's an MPS. It's not in canonical form. But I want to put it back in canonical form. So now I have this guy. What I can do is I do the contraction. Okay, it's a cheap contraction here. I don't have tons of legs, so I can just sum over the legs here and get a single tensor like this. Okay, this step should be fairly clear. And now I SVD. And what I get is something like this. Like U tilde n, lambda n, Vn. DAG. So here it's lambda tilde n. It's a new lambda n, if you like. So I should put tilde everywhere. There are the new ones. And I have to put it back in canonical form. So what I do, like before, is that I will add lambda n minus 1, lambda n minus 1, minus 1. So here I did nothing. I just added identities here that I split from a matrix and its inverse. It's just to get back that now I group like this. And I get, and this, if you like, is my new gamma. Sorry, I should say okay. And now I'm back to the canonical form after having done that. Of course, there is a problem that if lambda n was size d, well, now lambda tilde n is of size d times d. You should see it from here, okay? Because here these legs have dimension d, d, and small d here. So by applying this gate, I increased the bond dimension. I multiply it by a factor that is the physical dimension. So TBD like this without truncation is unsustainable. That would again grow exponentially. But what you do is then, since the state is in canonical form, we know truncating the singular values is the right way to truncate it. Okay, it's an efficient local way to truncate it. So now you truncate lambda tilde n to, I don't know how to call it, tilde n. Sorry, lambda tilde trunc. That is of size, say d max, the maximum bond dimension you're willing to allow. So maybe at the beginning, your bond dimension is, say, 2. You will run TBD. The bond dimension is going to increase. And at some point, you saturate. You will just truncate the singular values that you cannot afford. In which case, do you have a small error? Well, now all our previous analysis is for free here. I mean, the theory analysis we did before, we can use it. So we have a small error if entanglement remains small. Okay? But okay, I'm not really answering the question. So when does the entanglement remain small in this kind of real-time evolution? Okay, maybe I'll let you. So you get this setup that we evolve like this, and that generically the bond dimension grows. But of course, if we can guarantee that during the evolution entanglement remains small between every possible cut within the system, then we are guaranteed that this doesn't make a big error for d max large enough, okay? But doesn't for d max that is not exponential in the size. So one thing is that if you start from low energy, so you start from, say, a small perturbation of the ground state of this Hamiltonian generating the evolution. Then we know that the evolution will remain supported on low energy eigenstates. And low energy eigenstates are weakly entangled. They are also verifying the area law. So in that case, if you start from, you also have low entanglement. And so this is efficient. And you can do very long time. Okay, so if the energy you've injected in your system is little, then entanglement doesn't grow much. And so TBD is an efficient way to evolve the system even for long times. Now, where it breaks is if you inject an extensive amount of energy. So what I mean by that is that the amount of energy you inject in the system is proportional to its size. Or rather, if you like, you increase the energy density and not just the energy. You increase the average energy density in your system. Sometimes this is called a global quench. Because one way to do this is you start from a ground state of a certain Hamiltonian, and now you change the Hamiltonian globally for the evolution. You, for example, change the magnetic field in the entirety of your system. So for these global quenches, what you can show is that, say, the bipartite entanglement entropy grows proportionally with time in the system, and it saturates at n. So it saturates at volume law, okay, at something of order n. So okay. And so what that means is that your TBD simulation will be accurate for a short time, and then entanglement will be too much, and you will not be able to simulate. What is crucial, and that you should have in mind, is that S max, the maximum entanglement entropy you can get, is something proportional to log D. Okay, so by growing D, you don't go much further in time. That's the crucial thing. So if you like, if you double D, you get a constant amount of time. Let's say you can go to a certain, I don't know, time 4 at bound dimension 10. Maybe then you go to 20, you go to 5. Okay, you go to 40, you go to 6. You have to grow your bound dimension exponentially to reach only linearly more time. So in practice, you will not go much further with a supercomputer than with a laptop on this kind of problem. And I will say more about the link with quantum supremacy later, but it's the same for random gates. So if you put random 2-qubit gates, typically you have the same, that the entanglement entropy is proportional to time, so it grows linearly, and saturate to volume law. And so that's why typically Google and people put themselves in this situation. Random unitaries create entanglement very fast, and so they are particularly difficult for tensor network methods because they generate extremely slowly decaying singular value even at low depths. So like that's one of the reasons. Of course, you can still do it. You can still say, okay, I mean, asymptotically it's not going to work, but the world is not asymptotic. The processor of Google is finite, okay, so I can still try it. And that's what Zhu, Studenmeyer, and Vantal did. And it still allows to simulate pretty large circuits with pretty good fidelities. Okay, I will stay vague like this. Pretty large circuits with pretty good fidelity. And just why I insist on fidelity, what is the main trick that they use in this paper? It's that, here we are going to truncate, so we're going to make an error. But when you apply gates on a NISQ device, you also make errors. And before, people were trying to simulate this quantum evolution exactly. So this means that you cannot tolerate to truncate your singular values. But now you can say, okay, I accept a level of truncation. That means that my 2-qubit gate error is the same as the one they make on average. And if their 2-qubit gates are not so good, this allows you to truncate a ton of singular values and massively reduce entanglement in your simulation. And that's also what shows that for these systems, what is really crucial, in fact, there is a phase transition, a point at which if your fidelity is good enough, then the entanglement really starts to grow even if you make the system bigger. But if your fidelity is not large enough, even for 1,000,000 qubits, the TBD will manage to simulate with the same fidelity, okay, because it can cut the amount of entanglement. And there is a phase transition with your fidelity of gates. For this problem, of course, when I say phase transition, it's assuming infinitely large systems and everything. So in practice, the devil is in the detail, and it matters precisely what amounts of errors you have, how big your system is, how square is it, or rectangular it is, okay. But I will go back to it at the end, but just already to show the limitation. So you see, this allows us to do real-time evolution. In fact, we could also use it to optimize our state by now running imaginary time evolution. So remove the I here, and that would project to the ground state. Of course, this would no longer be runnable on a quantum computer. The gates are no longer unitaries, but we could still essentially use this algorithm, TBD in imaginary time, and that's a popular optimization method, but essentially DMRG is more efficient. So now I will explain what you should do if you want to find now the ground state of a system. And the ground state can be useful if only to find an initial state to run your time evolution, because in some cases, you know that your initial state is, say, the stationary state or the low energy state of some system, but maybe you don't characterize your system very well. So maybe you cannot, write this initial state very well. Maybe it's not a product state, so you need to find it with the MRG. Maybe other question first on TBD. So showing the phase transition. So there is a very recent paper by the Google team, like discussing on their new Sycamore 70 that they are really in the volume law phase of the setup by having reduced, and they add a lot of theory arguments to substantiate this, like to really say, okay, we are in the volume law, and so these techniques would really fail. Okay, this is a preprint. The latest preprint from Google, like from 3-4 days ago, I would say. Yeah. I mean, of course, there is a lot of theory in general on these phase transitions, but that's, I would say, the most recent and the most closely related to what we're discussing now. Okay. So now I'm going to tell you about DMRG, the modern way. So I'm going to present you DMRG, which means density matrix renormalization group. The modern way. So it's not how it was introduced first, with matrix product operators. Well, because it's a more tensor network way, and it's probably the way you're going to encounter in the literature. And this is an excuse also to introduce a new concept, the concept of matrix product operator, which is going to be very natural. Okay, so now we'll want to evaluate the Hamiltonian of our problem, a local Hamiltonian. And so for a local Hamiltonian is something that typically looks like this. That is, it's the identity, and then on two sides it acts non-trivially, and then it's the identity. Okay, so what I'm saying here is like, essentially I'm writing that it's a sum over k of hk, where this hk is a tensor product, as a tensor product structure. Okay. But what is pretty annoying is that this h is a sum of tensors. Okay, let's scratch this. This is a equivalent. This is a sum of tensors. And that's going to be a bit inconvenient for us to have sums, and so we would like to write this in a much more tensor network way. And it turns out that for local Hamiltonians, you can always do it exactly, and for non-local Hamiltonians, you can sometimes do it approximately. Write it in MPO form. That is like this. So now it's a matrix product operator. I guess the generalization is pretty natural from MPS. Like we have, it's a matrix in the physical Hilbert space, this object. Okay? And what I'm claiming is that this step, that maybe we can call MPO compression, it's exact for local H. But yes, so I can always find a representation of such Hamiltonian in MPO. And I'm going to lie a bit in the sense that I'm going to, not lie, but I'm going to not prove it because it's a bit tedious. I'm going to illustrate on an example how you could find it, okay? On the example of the Ising model. So that's clear what I want to do. So I want to write a local Hamiltonian of your problem. I want to write it in MPO form, in this form of a tensor network as well. But the stark contrast is that finding the best matrix product state representation of a ground state, this is an approximate operation, and that requires complicated algorithm. Writing the Hamiltonian itself is something exact. It doesn't, and it's something you can do with that you can do analytically usually. So I will not show the general idea, but you can, from one example, you can derive essentially, you can get the intuition for the general way to do it. So I'm going to just consider the quantum Ising model. And my objective is to show you a matrix product operator that gives this Hamiltonian when I uncompact it. Okay, so we are back to a few minutes of tricky, just so that you have to turn your brain back on for a tiny bit for this step. So what I will just exhibit what tensor I have to put here so that it gives this, okay? And for that, I have to tell you how this tensor is represented. It's a tensor with 4 legs, okay? So now think about it, a tensor with 4 legs. Let's say you were to represent it as a NumPy array. One way to do it is to write a matrix of matrices that would give 4 legs, okay? And that's precisely what I'm going to do. So here, I'm going to have I and j. They are going to be the line and columns of my macro matrix. And then the entries I'm going to put in this macro matrix are going to be operator acting in this direction. So it's a matrix of matrices, and I'm going to write it like this. So I this is on-site k, sorry, because it's a different operator on each site. Okay, so it is this matrix product operator has bond dimension 3. Okay, that's the size of this macro matrix. And the entries you see are operator acting in the physical Hilbert space, in the vertical physical direction. Okay, so right now I'm not saying why it's obvious that it works, okay? And then I should give the boundary ones. So the boundary ones are vectors. Oh, it's J, sorry. Okay, and so now what is happening here? Okay. Well, when we stack these together and connect them, we are doing the matrix product in this macro matrix space. Okay. So if I now put, and I didn't even, if I now put two of these tensors together and connect, it's going to multiply these two macro matrices. And what you're going to see is that this sigma k x square root j of the left matrix is going to multiply with the one of the right matrix and sum here and get summed here. And so here at the next step, we're going to get sigma k z plus sigma k plus 1z plus sigma k x plus 1. And if we multiply them for all the chain, except for the last sites, we're going to get precisely the Hamiltonian we are looking for on the top corner, on the top right corner. Okay, I mean, unfortunately, that's something you have to do, okay, to see. But what I'm claiming is that indeed, if you do the product on these ij indices, you now get an operator acting like this on the corner here, and then these are just to choose this coefficient here, okay? Anyway, I mean, we can be nasty and say that exercise verify it. And more generally, you can realize that you can construct larger, if you had like, say, next nearest neighbor terms or more operators, you just have to enlarge your matrix, put more entries like this, and make them in such a way that then they will accumulate here, and then select this coefficient. So that's one way to produce this MPO. It's actually not the only one. But what we care about is that this is fairly simple in practice to find an exact MPO. But it's a bit stronger than that, is that this form also contains exactly Hamiltonians that are not strictly local. So Hamiltonians that are exponentially decaying, for example, with here not a sum on nearest neighbors, but exponentially decaying would also be feasible. The only thing that you cannot do is large, like slow decay, like power law decay. This you can only approximate as a sum of exponential decays. But it can still be a pretty good approximation in practice. And in which case, it's not an exact MPO compression, but an approximate MPO compression. This MPO is a way to, so here we are using already for something that's local, but for an interaction that is not strictly local, that's a way to localize it, at least in tensor network form, and use this MPO bond dimension as a way to recreate the extension. Of course, the price to pay is that if you want to improve the quality of your approximation, this MPO bond dimension would increase generically. But here you see it's fixed, it's 3, it's a fixed number that we are not scaling, like we are exact already at 3 for this Ising Hamiltonian. Okay, so now we can move finally to DMRG proper in a way. And again, we have made all the effort such that now it's going to be easy. The idea of DMRG is that we evaluate the expectation value of the Hamiltonian, and we will swipe over tensors to optimize it. And we are going to choose a mixed canonical form. So here I'm going to do something a bit nasty, is that this is the DMRG algorithm is an algorithm where you iterate, you swipe through your chain. So it's something, I should show you the first step. I'm just going to show you a step in the middle. Okay. And we are going to understand, of course, how it could be done. And I'm going to choose a mixed canonical form like this. Okay, so that's the expectation value of the energy. And what we want to do now is we will want to optimize these two sites. We will do it iteratively. We will not try to optimize all the sites, all the tensors at once. We will first try to optimize these two tensors. And here it's the conjugate, okay. Well, this, if you focus only on the two tensors, here you see two ladders that we can contract efficiently in left and right environment. Okay, so that's the first step. We contract the sides into left and right environments, which again is something that is not expensive. When I say not expensive, I always mean over d cube doesn't have a cost that is exponential in the system size. And what we can see is that this problem is like we can group our two tensors, the tensor we want to optimize over, in just one tensor, x. So one is x, one is x star, if you like. Okay, so to go from here to here, I contract the sides. To go from here to here, I just block the two tensors. And now, what is crucial is that this is a quadratic form applied. So, okay, I will say you have this map now T. Now you see this map appears here. So this is just, this object is in a way like x, t, x, where I've defined the map t here. Right? It's something that has, so how do I minimize this? I should say also, because we were careful in all these choices of gauge and everything, this guy is self-adjoint. And so how do we minimize this expression? We just find the lowest eigenvector of t. Okay, we have that the x best, if you like, the one that will lower the energy the most, is the eigenvector of t with smallest eigenvalue. And so we can find it by diagonalizing t, for example. In fact, we don't even need to diagonalize t. We can just use an iterative algorithm like Long-Shaw's to find the lowest eigenvalue. So typically, you find the x best with Long-Shaw's or any other diagonalization technique, sparse diagonalization technique. And in practice, of course, you have to be smart in the way you apply this matrix to your vector to get the lowest cost as a power of d. Okay, fully diagonalizing it would be not smart in a way because you would have a cost too high as a function of d. But okay, that's in a way technicalities that are easy to get right. At the end of the day, what is crucial is that as a function of the bond dimension, capital D, nothing should ever be more costly than d cubed. And then for this version, and then the cost as a function of the physical bond dimension d, this one depends on the algorithm. Here it would be d squared. But the cost of the steps, what is crucial, what gets big, okay, in practice is the bond dimension. And the cost of all these steps is d cubed in the bond dimension. So once you found your x best, we will do, I mean, this is almost always the same thing, right? The issue is that now it's no longer in the form we want. Yeah.
Is it obvious that it is d cubed?
Because applying it to a vector is of course d cubed.
Okay.
No, I should, okay, is it obvious here? So yeah, one should see that applying this to a vector, the operation matrix vector is of course d cubed. Because it's a good question. Because at the end you are multiplying matrices on the d bond, and this has a cost d cubed. More generally, actually, computing the environment as a cost d cubed, something you can. When I say d cubed, I really mean there is also a power of the physical dimension that enters, but I'm only talking about the bond dimension cost. But yeah, this is d cubed for all these algorithms. So once you found it, and you can got careful to construct in the right order to be in d cubed, well, you SVD it, okay, x best, and you get something like this, where u vdag lambda. As before, you have this problem that now lambda here has d times d singular values. And so what you do is that you truncate to d max whatever you are willing to accept as your bond dimension. Often it's just the same, you know, you are going to stay at the same bond dimension as you started, if you like. But what is nice with this algorithm is that it allows to dynamically increase the bond dimension. So you started with an MPS, maybe a very low bond dimension, and with this routine, you can go to d times d, and this is a way to progressively grow the bond dimension without necessarily having started at a very high bond dimension. Truncate. So now we truncate, we get something like this, still the same form. And now we group. Now we group like this. Yeah, I should say, yeah, we group like this to get now something like this. And since we grouped like this, ooh, that's, yes, okay, that's what I want. So here it was like this in my color code. So with the grouping I did, now it's like this. Only this guy is an isometry. And now you should, so this is what we just did is one step of the DMRG algorithm, one local optimization. What did we do? For one is that we found, we optimized two sites together. But also, I was careful at this last step. We moved the white center to the right. Okay, so initially, what I optimized here was white, red. And now I have blue, white. So in the chain, now, if you look at the initial thing, now the white moved by one notch. Okay. Well, because of this, now I iterate. I apply it again on the white-red block, which has shifted by 1 on the right. Is that clear? That because I now chose to group this way, I moved the side to the right. And so I can just keep on. I will do it iteratively on the chain. And once I arrive at the end, I just go back the other way. Okay, I mean, if now you reverse, you symmetrize the picture, it's clear you can also run this algorithm leftward. Okay, everything is the same the other way. And so you iterate, and you do what people call sometimes left and right swipes. You do in swipes. And the algorithm is a sort of iterated least square. Okay, at each step you optimize 2 sides together to get the best, and you keep on, and you go back. And what is important is every time you do this, you are sure to reduce the energy. Okay, because this expectation value is the expectation value of the total energy. So we are sure we go down every time. But of course, at least, sorry, if we didn't truncate here, at least we're sure we go down. But of course, there is no guarantee a priori that we converge after these sweeps. Okay. Okay, I say swipes is sweeps. Sorry. Sweeps, we sweep through, and yeah, so in practice, what we see is that only a few are sufficient. Okay, like you go through the chain a couple of times, and the energy is super well converged. What happens is that if the system is close to a critical point, and the gap is very small, it can take a lot of sweeps to converge, but say in practice, this is not really an issue. Okay. Okay, so that's all for the MPS algorithm, and then I will say a bit more quickly about 2 dimensions, and then about link with supremacy. So maybe we should just, if there are questions about this first.
Yeah, a stupid question, but is there an interpretation to, like, in terms of mean field, it's when you contract the left and right part, and you optimize over the two body?
Yeah, you really, I see it as really an environment interpretation. Like you're really taking into account all the environments so that you really are optimizing over the reduced density matrix and not some fake things. Okay, you're really taking into account the environment around the tensors. I don't know if that's maybe not the best way to formulate it, but yeah. So, anyways, the emergent algorithm can be, I should say, also extended in many ways. So, you see here we are on the finite systems and the tensors are in principle different, but you can do translation invariant and have all the tensors the same. This is called. You can also do translation invariant. So, if you ever need it. It's in a way easier. And the algorithm is called VUMS for variational uniform matrix product state. Which allows you to deal with translation invariant problems. Okay, so we did a story mostly of the 1D case. Here you see MPS. And it's a very nice story because we have it's a very appealing story. We have strong theoretical guarantees that we have the right manifold of states. We have efficient algorithms to then find the right states within this manifold. And in practice, the end product, say after DMRG for a sufficiently kind problem, is typically a numerically exact solution, okay? That is quoted as such in many papers. So this is really a success story, the 1D. Like there is, essentially it's nailed entirely. But so we have, I mean, it would be dishonest to not mention the difficulty in going to higher dimension. So if we go beyond MPS, what we'll see is that at a bird's eye view, things are the same, but in the details, everything is much more difficult. Okay. So 2D and more. Essentially, you understand the problems already by going to 2D, and then they are the same. They are just even worse in 3D, but it's the same kind of problem. The first, and I want to list the problem, tell you how they are solved usually, or approximately solved. And so sort of give you a very, very crude idea of what's the status for that. So, okay, so I write the state in 2D. Remember, we made our construction fully general at the beginning. And so we saw what were these tensor networks in 2D. They are objects like this. The 2D PEPs, two-dimensional generalization of MPS. And so just to write them, there is no difficulty. Okay, like you can write them pretty easily. Now, the problem is that there is no exact contraction routine. So what you want typically to do is, remember, the first thing we did with MPS was compute the expectation value of the identity, the norm, with the ladder technique. And remember that because of the ladder technique, it is a cheap thing to do. So now I will draw. This is the elementary, if I contract psi with itself, the elementary tensor in the contraction looks like this. So you have to imagine that now this keeps on the plane, and this keeps on the upper plane. Like the ket will contribute tensors like this, and the bra tensors like this. Is it clear that at the end of the day, if I compute the norm, I'm going to contract object like this. I'm going to contract this. Okay, this sheet with the other sheet here. And so the elementary tensor in this double sheet is something like this. In this sandwich, okay, in this PEP sandwich. And that, if I contract it, it's an object like this. If I just contract it as one tensor. And now I'm going to say, okay, I'm going to group these legs and now just say that this is a tensor like this. Such that at the end of the day, by fusing these two indices and contracting the physical index, this is something I can write again in 2D. And it's something like that. Okay, is that clear? That's the flattened sandwich that gives me the expectation value that I obtained by taking two bra and ket like this, contracting the physical index. This to this? Yes. I just say that the new Hilbert space here is the tensor product of the. This is cheating. If you like, there are fatter legs. Okay, they live in a bigger Hilbert space. Okay, now it's d. So if these were, sorry, if it was d, here these legs are d squared. And the thing to see is that now the ladder trick doesn't work. And so let's say I want to contract this way. Well, this extends to very far, and so the dimension, the map here, acts in an exponentially large Hilbert space. Okay, so just to say, before, if I had done this kind of fusion of legs for MPS, the ladder was just this. In this notation. This was the MPS ladder, if you like, where I contracted the physical index. Here I have something like this, okay, that extends a lot. And so the dimension, the map I should iterate, in principle, is this. This is my transfer operator T. But you have to imagine, okay, it's very big. And this transfer operator has a big dimension. It's like d 2 square root n, the dimension here. I mean, if I have a square with n. And in fact, this is generic. So this is, I'm suggesting one contraction technique, trying to get this number by contracting this tensor network from left to right. But in fact, this is fully general to whatever technique. This can be proved that contracting a two-dimensional tensor network exactly is in general unfeasible. Like, it's a hard problem. And basically, the general argument is that if you have your PEPs like this, and let's say you don't contract it with the ladder technique, but you contract it iteratively by the way to contract this progressively will be to, you start by contracting two tensors together, then you add the third, then you add the fourth, okay, and then you add tensors one by one. I mean, that's the only thing you can do to contract. And at some point, your system is going to be cut in two between what you already contracted and what you still have to contract. And this has to cut many bonds, okay? Also, at some point, when you arrive roughly in the middle of your contraction, this necessarily will have of order root n open leg, no matter how you do it. So there is no way to contract these tensors by keeping at all time only a small number of open legs. That's the argument essentially for why it's very difficult. And you see that this is a big problem because this we use it all the time, this ability to contract a tensor network. And so if we cannot do it in 2D, is it dead? Okay, that's something we might worry, that we cannot get anything. It turns out that approximate contraction is good. Approximate. Yeah. Sorry?
Can you just repeat why we cannot get it in 2D?
Yes, so do you get why this contraction technique, as we did before, contracting this way is expensive? Yeah. So I'm just saying that if we do it more generally by, say, starting with one tensor, then I add one tensor, I contract it, now I have a block. Then I add a new tensor, whichever, And let's say I try to choose a smart order, maybe to do it better. At some point, I will reach a situation where I have contracted roughly half of the tensors in my block. What I'm saying is that the border, the frontier of this region will have square root n legs open, roughly. Okay. So in the course of contracting from one to everything, necessarily at some point I will reach a point where I have many open legs. There is no way to contract this in a way that you always keep few legs open. Few legs open means few parameters you are storing at a given time. But okay, so I just want to say that approximate methods work. And so in practice, one way to compute this is to say, okay, actually, you can interpret this contraction of the PEPs as something like this. So this technique I'm showing is the technique called boundary matrix product states. My PEPS contraction, my 2D contraction, I can see it here as an MPS. MPS. Now evolved with an MPO, on which I apply an MPO many times. And of course, every time I apply an MPO, I increase the bond dimension. But then I can put in canonical form, truncate, and keep on. You know, I can do an approximate contraction of this by seeing it as some kind of imaginary time evolution of this MPS with successive MPOs. And compress at each step, because I will compress. I have no choice. What we see is that for practical problem, the compression, this compression for PEPs that occur in physical problems, this compression works. And that there is small error by contracting approximately with an MPS, evolving it, then putting it in canonical form, truncating, evolving. Okay, that's just one of the ways to do it. That's sort of, I mention it because it's the closest to what we've been doing so far. But what happens is that you see that these approximate methods are essentially reducing the dimension by 1. And at each step you want to compute an expectation value in 2D, you have to solve a full MPS problem in 1D. Okay, so it's the price of each iteration of your algorithm in 2D is a full algorithm in 1D. Okay, so you understand already why it's much more expensive. I give you, so this is one difficulty. You see it's solved practically that we can compute approximately expectation values, but still it comes, this practical solution comes with a huge increase in cost. The second problem is that there are no canonical form. For PEPs. So you cannot reliably truncate a PEPs, a two-dimensional tensor network, just by killing some singular values that you don't care about, because this form in full generality doesn't exist. And so it means that the easy algorithms are less reliable. The easy algorithms that we saw today, like TBD, are less reliable for PEPs. Because we don't have the same guarantees on truncation, on local truncation. And so that means, in principle, to be really reliable, you have to use the full thing, like real gradient descent on Hilbert space. So like TDVP stuff, full things where you don't just work locally, but approximate efficiently the full environment. And finally, the biggest theoretical problem, in a way, is that there is no proof that it works, in a way. Like that, no proof that of efficiency. Like there is no proof that PEPs, the kind of proofs we saw, kind of rigorous results we saw by Sirac-Verstraete, Hastings, that this works, they don't exist for PEPs. So what we have is that, of course, there is still the area law, so all this area law intuition remains valid, but the formal arguments no longer are. So now it's just, the folklore is that it works. The numerical folklore is that we see it works, but of course that's much less secure than for MPS. Okay, in practice, what it means, okay, just to do a summary of what this implies, that in 1D, again, let's say for gapped all the time, you can reach, in many cases, machine precision. In 2D with PEPs, you can reach the state of the art for many problems, but clearly not solve to machine precision for no model. You can get maybe 2, 3 digits, or you're going to get close or better than the best methods, depending on the problem, but it's not, you cannot say that the problem is completely crushed or solved exactly. And in 3D, you struggle right now. I mean, there are some people have tried, but in particular, so yeah, one of the biggest progress, most accurate algorithm was pushed by people like Philippe Corbeau and others. And while they really made insane progress on that stuff, you struggle, sorry. So in 3D, there are some things, but say the max you can do is bond dimension 2 or 3 because the cost is insane. So 3D, which is in a way the ultimate target, the real world of quantum matter physics, is out of reach. But 2D was thought to be impossible, and now 2D is routinely done, so it may change. I should say that because of the difficulty of these two-dimensional tensor network algorithms in 2D, people have used there are a number of, I would say, degraded methods that still work, that don't verify the area law, for example, but that can be used in practice in a way that they are much simpler. You have, could I just briefly mention these alternatives, because let's say if you have a problem of finite size that may be used, that may be usable for you. So what you can do is you just do an MPS in 1D for your 2D problem. So let's say you have a lattice. Like this. Okay. What you can do is just group the sides vertically and build an MPS like this. Okay. This is not magical. You don't, but you get a cost exponential root n, which can be, in some cases, enough to make your problem runnable. And you have the advantage that you use all the extremely well understood technology of MPS for your problem. For example, if we think again of these supremacy simulations they were done with MPS, even though the Google chip is 2D. And they essentially write an MPS like this. Okay, if n equals 40, root n is small. Okay, so that's actually these algorithms were the only game in town for 2D before the PEPS algorithm started working, and I would say now we have reached the point probably where now the true 2D algorithms for ground state search behave better, but even it's not fully clear. I mean, I think it's really problem dependent. That this approach on a finite system, but as large as you can get, is already pretty good. You can, when you start these things, you are like, why not do a snake MPS, for example? That is, you go through your system like this. Okay, that's an option. And of course, this is very inefficient. Okay, you probably see why. Is that clear what I mean by that? That my sites are like this, and I just construct a 1D MPS from this. Well, of course, the problem is that you can look at it here. For example, I mean, these two sites, they are close geometrically, so they are fairly entangled. But now, this entanglement has to go through all the chain to connect them. what you can also verify easily is that this doesn't verify the area law, because if I take a region, the number of lines I cut is never going to be proportional to the area, to the perimeter, in that case of the region. But again, okay, in some cases people use that for small enough problems where we don't really care about asymptotics, and got fairly decent results. And finally, one thing, I will put it here, that has been used, that is quite popular, are trees. So I write the tree in 1D, but it's clear that it works in every dimension. So you write a tensor like this, tensor network like this. Okay, imagine this generalized in 2D that covers a 2D space. And this has the advantage that it's efficiently contractible. So you can always compute expectation values with this tensor. But again, it has no area law. So it's good for small, medium size. Okay. So of course, if your system becomes very large, you're going to have to put extremely large bonds here for your tensor network to produce the state. Okay, so that's all about larger dimensions. And now I wanted to conclude. I mean, because most people here are interested in, I think, ultimately by the link with quantum computing and some supremacy problems. What can we do with tensor network? Can we not? What can we not do? I think one way, like our little exploration was useful, is that I think we have now a much better understanding of when tensor networks work and when they don't, and when they are easy to implement and when they are difficult. And from the complement of that, you more or less see what quantum computers are going to be good at and what they are going to be useless at or less useful at. Okay? And so I just wanted to, before finishing, like just summarize the implications for quantum advantage. Not really quantum advantage. Okay, yeah, let's use quantum advantage, but I don't mean necessarily something useful at that stage. And just tell you from what we saw what is good and what is bad for quantum advantage in a given platform or for a problem you're looking at. Okay? So what is good to get an advantage is to have a lot of connectivity. Say 2D or even more, or maybe infinite. Like if you can do gates in 2D with a 2D locality, like 2-qubit gates on a, you clearly are making life hard for tensor network methods, because now they have to use this degraded impulse form or use two-dimensional tensor networks. You should do real time and run real time for long. What I mean by that is that you should solve problems where you're interested in the time evolution. And you should have a lot of entanglement. And so typically look at global quench. Like a lot of energy injection. So in the language of gates, usually it's like random gates that entangle extremely quickly the system. But what is, and I mean, this is just going to be sort of the reverse of what I wrote here. I mean, if you have 1D connectivity, already you make it much easier for tensors. So if you're cheap, if your logical qubits are in 1D, this is easier. Or say your physical qubits are in 1D, it's much easier to simulate. If you are targeting ground state problems, or low energy problem. So I mean, like by opposition to real-time evolution, like static problem, you're interested in the thermal quantities or low energy quantities. Here, there is not even any reason to believe that quantum computers have an asymptotic advantage. Okay, it's not even. These states are area low entangled. They seem to be efficiently representable classically, at least when they are representable. And there are some ground state problems that you hide in the ground state, say a combinatorially hard problem. In that case, it's going to be hard for everyone. And there is no reason to be sure that, or to think that quantum computers would be substantially faster. And say for physical problems we care about, it's not so clear. Okay, so ground states, this kind of ground state problem are. I'm not saying there will never be an advantage. Okay, I'm just saying if you are doing real time with entanglement, clearly you are in a regime where we know it's hard. Okay, so it's very different. Okay, I mean more generally, these second lines are a bit redundant, but like everything that is area low entangled, no matter how you reach it, through evolutions, through something static, is through the fact that you have weak low fidelity. Okay, if you have low fidelity per gate, you are also going to reduce your entanglement, and so you are also going to be in area low, in area state. And so what that gives you is that I think in the NISQ era, if you want to compare tensor networks and quantum computer, really details matter. Like you cannot just be asymptotic because everything is going to be finite. And what is crucial to compare and to have in mind is that for real-time evolution with global quench on finite devices or with tensor networks, both methods are exponentially inefficient. Okay, a NISQ quantum computer has an error that increases exponentially with depth, and the cost of the SVD of the bond dimension we do also increases exponentially with depth in the volume law phase. So both methods, NISQ and tensor networks, are exponentially inefficient methods, say, for real-time problem. The question is which is the least inefficient? And for that, in practice, the question is what is the truncation error you make with your SVD? That's the tensor network side, and that you have to compare with your 2-qubit gate error. On your platform. And usually, in most of the time, we are in a regime where increasing the size is not the crucial part. Like reducing the 2-qubit gate error is really what makes the tensor network method struggle. Okay. Okay, so that's all I had to say about tensor network. That concludes the review of why they work, the algorithms, a bit of 2D, and what they say about quantum computers. So if you have any questions.